on Learning Target 9, Exponential Growth and Exponential Decay. One example of that is HalfLife with radioactive substances. We're going to look at that later on in this lesson. The first thing we're going to look at here is exponential growth. Things that not only grow at a constant rate, but they grow exponentially. And what happens with an exponential growth equation is we start with an initial amount, a, and our base factor to the x is growing greater than 1. So if you look at this as a percent, we're growing greater than 100%. So for example, population might be growing at 5% each year. That means that it's growing 105% as the previous year. We look at a growth base factor when we were doing the paper folding of 2, where things were doubling. And that is definitely greater than 1. So that is exponential growth. Please note this equation. This is our foundation that we're going to build on in each of our examples today, with our initial amount here, our base, which is going to be either our percent or how it's growing, doubling, tripling, and then the exponent is going to be our x value. Here's an example. In 1990, Florida's population was about 13 million. Since 1990, the state's population has grown 1.7% each year. This means that Florida's population is growing exponentially. To find Florida's population in 1991, we need to multiply the population by 1.7% and add it to the 1990 population. And then we need to do that each year after that. So you would add 1.7% on top of what's already there, making it 1.7% added to 100%. That means our population is growing at 101.7% of the previous year. So here's a function that would model that situation. We notice here that we have our initial amount. That's our A value, population in millions. Our growth factor is 101.7%. We write that as a decimal, 1.017. Here it is as a percent. And then x is our number of years since 1990. So we're going to use that equation. And we could use it to find what the population would be today. So our following is a general rule for modeling exponential growth. Our starting amount, our growth factor to the exponent of x. Now keep in mind, because we're looking at exponential growth, our growth factor is always going to be greater than 1. Here's another example. Since 1985, the daily cost of patient care in community hospitals in the U.S. has increased 8.1% per year. In 85, such hospitals were at an average of $460 per day. So if we were to write an equation for this, we'd have y equals a times b to the x, where x is our number of years since 85, y is the total cost, a is our initial amount, which was 460, and b is our growth factor. Now it's growing 8.1%, so it's really 108.1% from the previous year. Notice, again, it needs to be greater than 1. So we get our equation 460 times 1.081 all to the x power. So if we want to approximate the cost per day in the year 2000, we would need to plug in 15, because that would be 15 years later. And when we plug in 15, we get $1,480. $1,480 is how the cost has increased. Now, when a bank pays interest on both the principal and the interest the account already has earned, the bank is paying what we call compound interest. An interest period is a length of time over which the interest is calculated. It could be per year, per month. There are different ways to calculate interest. Here's an example. Suppose your parents deposited $1,500 in an account paying 6.5% interest compounded annually. That means once a year when you were born. Find the account after how much is in there after 18 years. So you're about to go off to college or start your own life. You want to see how much money is in there. So go ahead and pause the movie, try writing your equation, and then press play again when you're ready. So we have the number of interest periods, the balance, our deposit of 1,500, our starting amount, and then it's growing at 106.5%. So we plug that in. We get 1,500 times 1.065, because it's 106.5%, written as a decimal, to the 18th power, because it's 18 years since. You will have $4,659.98. Not too bad. Would like that percent to be higher, right? Suppose the interest rate on the account was 8%. So here with 6.5%, you were getting $4,659 after 18 years. If the percent increases to 8%, let's see how much you'll have after 18 years. Pause the movie, try this on your own, and then press play when you're finished. All right, so we plug in 1,500, our starting amount. It's growing 1.08. That's 108%. And it's to the x power, x being the number of years. So we're going to plug in 18 for that. And we get $5,900. So we're close to $6,000 here just by increasing the percentage rate. Not too bad. Now, sometimes the compound interest is not per year. It might be monthly or quarterly. In that case, our formula changes slightly. We take our P, our principal amount, and then we do have 1 plus still because it's 100% in addition to what we're adding in the interest. But now it's R, which is our interest rate, divided by the number of times we're going to compound it per year. So we have to divide by n inside here. And then it's to the power of n, number of times we compound per year, times the time in years. So keep that formula in front of you. And let's try this problem. Suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest compounded quarterly. So this fact that we are compounding it quarterly makes things just a little bit more complicated. So what will the account balance be after 18 years? So we have to account for the fact that it's going to be compounded quarterly. We're going to use the compound interest formula, and the quarterly means 4 times per year. So we have our starting amount, 2,000, parentheses, 1 plus. Now this is 0.045 because I've not added the 1 yet. You don't do that yet. You divide this by 4 because you're going to compound it quarterly. And then it's to the power of 4 times 18 because we're going to do that for 18 years. So we're simplifying here what's in the parentheses, and then we're calculating, and you're going to get $4,475.53 after 18 years. Notice how the formula changed a bit because we were compounding quarterly. Another type of function is not exponential growth, but exponential decay. So in this example, we have the graph looks this way because it's decreasing exponentially rather than increasing exponentially. What's different in the equation for exponential decay is that our B, our base amount, is a decay factor of less than 1. So if you look here, we have B is going to be between 0 and 1 because it's decreasing. So if you think of taking 56% of something, you're not going to take all of it. You're taking a part of it. So it's the same thing here. The B value is decreasing, and it will be decreasing exponentially. So the formula will look the same. It's just the B value will change. So graphs show exponential growth and exponential decay. Here's growth, growing exponential, decaying exponentially. You'll notice it's getting closer to 0. It's not going into the negatives. Many times that doesn't make any sense to go into the negatives in real life. So we're looking at as x increases, y is increasing for growth, and as x increases, y is decreasing exponentially for decay. So real life examples include radioactive decay. Marie Curie of 1867 to 1934 received a Nobel Prize in physics and chemistry for her pioneering work with radioactive elements. Curie, a unit of radioactivity, is named for her and her discoveries. So half-life of a radioactive substance is the length of time it takes for 1/2 of the substance to decay into another substance. To treat some forms of cancer, doctors use radioactive iodine. The half-life of iodine is 8 days. The patient receives 12 millicuries of treatment. How much iodine 131 is left after 16 days? So after 16 days, there are two 8-day half-lives. After one half-life, there would be 6 millicuries left. After two half-lives, there are 3 millicuries left. That's sort of your thought process with how you would look at half-life. We can also use equations for that. So the equation for exponential decay includes our starting amount, our base factor, which is the decay between 0 and 1, all to the exponent of x. Please note the function a times b to the x is a model for both exponential decay as well as growth. The difference is what b evaluates to. It could be greater than 1 for growth and less than 1, between 0 and 1 for decay. Another thing to note, when a number is decreasing by 5%, the result means that you're taking 95% of the original number. If something like population is decreasing at 10%, then you're going to be taking 90% of what you have. If a population decreases at 15%, you're really taking 85%. So when you're finding the decay factor, instead of adding to 100, you're going to subtract from 100. Milk consumption. Since 1980, the number of gallons of whole milk consumption has decreased 4.1% each year. In 1980, each person drank an average of 16.5 gallons per year. So let's write an equation for that. So we have our initial amount, 16.5. Now the reason why our decay factor here is not 100 plus is because it's decreasing at 4.1%. So what I'm essentially doing is taking 100 and I am subtracting 4.1%. That's going to give me 95.9%, or written as a decimal, 0.959. That's what you use because this is decaying. It's not going to be greater than 1. We're going to use that equation to see how much would be consumed in the year 2000. So let me do this for you. Go ahead and pause the movie, try that, and then press play when you're ready. All right, so we are plugging in for x 20 because that's 20 years after. We get about 7.1. So the average annual milk consumption is about 7 gallons per person. Of course, discussion can start as to why, or maybe they're drinking alternative forms of calcium. Another example is in physics. So we have a kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101. For every 1,000 meter increase in altitude, the pressure decreases 11.5. So we're looking at decay. What is the approximate pressure at an altitude of 3,000? So we start with our exponential function. X is going to be the altitude, Y is the atmospheric pressure, A is the initial pressure, and B is our decay factor. So we're looking at 1 minus 0.115 because that is 11.5%, looking at it as a decimal. So we get about 0.885 as our base factor here. So we're writing that out with X. We use the equation to estimate the pressure at 3,000. So what we're going to do is plug in, it says for every 1,000, so we're going to plug in 3 for X, and we're going to get 70. So it's about 70 kilopascals. And that's it for this movie. I hope you enjoyed your lesson on exponential growth, exponential decay.